And then we're going to talk about some of these questions in red together. So you could halfway close your computer so that I know I got your complete attention. Take your earbuds out, put your phone in your pocket, it's distracting, whatnot. We're going to answer these from the Does Cold Exist article. So does cold exist? So you can write this either on your web quest or as a warm-up, but this gives you a chance to kind of make sure I know that you read and you understand what you read. And it's our introduction to heat. And so heat is not really a hugely new topic because you kind of already know a little bit about it because of phase changes and phase diagrams that we did, heat curves. It's just understanding how do I say something about heat, sounding intelligent, right? And that you actually know what you're talking about. So temperature and heat are not the same thing, and that's one of the biggest confusions. So look through, take a couple minutes and look at the questions, and then look through your Does Cold Exist article, which what's the answer to that? No. Does cold exist? No. No, because it's actually loss of heat. Okay, the loss of heat. So what is cold? Yeah.
It's just something that doesn't actually.
Absence of what kind of energy? Kinetic energies, right? So either I have a low amount of kinetic energy or I have a high amount of kinetic energy. So when someone's like, I'm cold, like, nope. You just have a low amount of kinetic energy, and then drop the mic. I mean, what else would you want to sound like? It's the best kind of thing to be, okay? So look at these questions and then take a minute to look through your article. It's going to be in the first page, of course. So what's the rule about how energy is transferred between two objects that are in contact? Raise your hand if you can tell me that. What's the rule about how energy is transferred between two objects when they're in contact? Andrew. Right, so I'm going to say high kinetic energy, high kinetic energy to low kinetic energy. Okay, now when that high kinetic energy is transferred to the low kinetic energy object, when does it stop? Yes. What's the, give me the full thing, the full word. Say it out loud. Thermal equilibrium. So this is going to happen until it reaches thermal equilibrium. Okay, so what does that even mean? Go for it, Jonathan. No, so there's an equal amount of heat exchange, but what's happening to the temperature at that time? It stays constant, right? The temperature stops changing because you have net thermal equilibrium. So there's no more temperature change. Okay? Now, does heat get lost?
Yeah.
No.
What's the law?
You cannot be transferred.
Boom! Okay, so he can either be can you say that one more time louder for the video?
It cannot be created or destroyed. It can only be transferred or changed during the process.
Wonderful. Great. So it's very similar to the law of conservation of matter, law of conservation of mass, in that it truly doesn't get, it's not gone. I mean, it's still here. If I'm holding a coffee cup and it's hot, where's it going? Into my hand, and I feel that, right? So it's transferred from one object to the other until my hand is burning hot and the coffee has dropped in temperature, but my hand has rose in temperature. So as one gives, one takes. What do you think that you would call that process of giving off energy? Yes, I'm hearing it. So give off energy. That would be exothermic. That would be in my scenario between cup and hand. What? What would be giving off energy? The cup is giving off energy, and then what's getting the energy? My hand, right? So to give off energy is an exothermic process. And we kind of say process because that's not a reaction, right? My hand's not like doubly replacing with the coffee cup. It'd be weird, it'd be odd. Okay, so we're just going to call it a process, not a reaction. So giving off energy versus getting, I'm using big words, right? Getting energy. Okay, so taking in energy. And that's going to be what kind of process? Endothermic, right. So we can think about that back and forth. Give me 1 second. So if I had to assign a sign, a positive or negative, to an exothermic process, what would that be? Negative, because heat is exiting, it's leaving the reaction or the process. And this one would be a positive because it's receiving, it's gaining, it's going into that process or that object. So we'll start to kind of look at it with the perspective in endo and exo. Yes, ma'am.
So, like in every reaction, there's always going to be an exothermic factor.
Yes, and it's actually something called system and surroundings, where in that example with the cup, this is a great coffee cup, big, huge, it's kind of a handle, and then I can. There we go. Okay, so this is losing energy, and this is gaining energy, because I have 3 fingers and a thumb. Okay, so it's losing energy, and this is gaining energy. And the idea is that it depends on your perspective. This is either the system or this is, it just depends on the perspective. Who keeps knocking my door? Santa. Okay. Where we look. Oh, okay, so to take a minute and look at the rest of these questions on the 3, 5, and 9. Do those right now. Take 2.
Yes.
I know. Alright, so second question, true or false?
False.
Third question, okay. It is false. Why? What's the true? I mean, what should be changed here to make it true? Not all particles. Okay. No, we can. Okay, I was looking for either one of those. This one's the more educated one. But yes, not all particles of a substance have the same kinetic energy. Because, I mean, yeah, we say they're all the same temperature, but the definition of temperature, maybe we should answer that one first, and we'll come back to that. What's the definition of temperature, number 4? Well, I meant 4 too. It's red. Okay. Average kinetic energy. That's as simple as you can make it. Temperature's definition, which was on your reading guide 17, is the average kinetic energy. So if average kinetic energy is related as a bell curve, didn't you see that bell curve kind of on the diagram? They basically were saying like, this is number of particles, and this was like energy, no, speed, right? Am I right?
Yeah.
Okay, so I'll let you know right before I move on. So some of these particles, which are at, I don't know, 25 degrees Celsius or something, they're over here at like 5 meters per second, and these are over here at like 500 meters per second. So in a given sample, I can have every single speed represented. That's because, you know, think about like bouncing against a wall. You kind of come back with a little less energy, or if you get a momentum and you can travel in a straight line, you're moving faster. So particles do the same thing. So there's a range of speeds they can take on, and that's kind of correlating to speed, aka kinetic energy here. So no, not all of them have the same speed, but what we say is that they have the same average speed if they're at a particular temperature. We kind of call that top of the bell curve the average. So we kind of break them into a group and then say you're the average. So related to that, no, not all of them have the same kinetic energy, but you could say they all have considered to have the same, which is the average kinetic energy. If you were to modify that right there. Okay, 3 kinds of motion. Get up. Get up. I want you to show it to me. All right, what's the first one?
Vibration.
I was going to go this one. Translation. Okay, and then?
Rotation.
Okay, rotation. So? And then like, no, I'm not jumping. Too old. And then vibration. Okay, good job. You can sit back down. I was really hoping you would say translation, rotation, vibration, and then act it out. I make my AP kids act this out, so.
That's a rotation, translation, vibration.
Yeah.
You're only like 20.
I can't get on the bowl anymore. Check out that website for homework. Thank you. Do real good. 4. Hit it on the green. Okay. That wasn't a pun. That was just normal encouragement.
No.
You guys are trying too hard now. Stop trying so hard. Let it come naturally.
Whenever the ball hits the,
Make the kinetic energy high.
So I'm thinking on my AP set.
oh.
The L.
That's what I'm thinking of all of them.
Alright, so you know, I'm just coming out and do this question now because you ruined that for me. I can't do it. That's not even an L. It's like a. So that's the worst kind of L you have to draw. Okay. Oh Lord. Okay, so pull it back of your computer. That's what I said, halfway closed. Go to part 3. I might be lying to you. It looks like this, where it says the link and it says calculate the specific heat of metal X and metal Y. Okay, so I believe is it the last part 2 or the beginning of 3?
Part 2.
Last of part 2. Okay. Of section 2 from the simulation, the web quest you've been working on. Yeah. So I'm gonna do a part of this right now. Not yet. No, I checked it. If I saw it and I said you were good, you got 100. Okay. Don't lose those because eventually we'll start to compile some of our work. Okay. So don't throw stuff away. All right. So I know I warned you far in advance. So what's the generic equation that solves for heat? Q MCAT, which is MC delta T. Okay, so this is heat that's associated with a given mass that's changing a certain temperature that has this thing called a specific heat capacity value. And this is just quantifying the amount of heat that a certain substance takes in or gives off when its temperature changes. So I could do that with my coffee cup. My coffee cup starts off at 100 degrees Celsius, which is really hot, and then it goes down to 30 degrees Celsius. Well, if I had 100 grams of coffee, I could actually figure out how much heat was lost or heat was gained in that case. So what I can do is, because an object like the coffee cup and the hand with weird thumb, okay, because of that situation where heat is transferred from one thing to another, I can actually say whatever heat was lost here is whatever here, gained here. And so isn't it the same energy? Yeah, it's the same thing because like it didn't come from nowhere, it came from somewhere because law of conservation of energy. So the heat that's lost from the cup is gained by the hand. Or if I was holding an ice cup, where would the heat be going? That's a hand. Little fingernails.
Wow.
Little fingernails now. Okay, so where if it was an ice cup, where would the heat go? To the cup from my hand. Okay, just trying to make it look like that. I get goofy on Fridays, guys. I just can't handle it. Okay, so in this case, heat is Q, heat is Q. Where would I assign the positive and where would I assign the negative? Positive on the hand and
Negative on that.
on the heat lost, right? So I can say heat of cup equals heat of hand, with a negative on this one, a positive on this one, to indicate the flow of energy. You with me so far?
Yeah.
Okay, what does Q equal?
MCAT.
MCAT. Can I now say MCAT equals? MCAT equals MCAT. This is the generic way of writing it when we're considering one system. Now I'm considering a system and a surrounding, so you can name them differently.
Could you do MCAT equals negative MCAT?
Yes, that's what we're going to do. Because this negative here, I have to keep the negative, but I'm going to put MCAT, MC delta T, is equal to MCAT, MC delta T, and I actually can find in a problem mass, specific heat, temperature. Mass, specific heat, temperature. And I can solve for one of these variables being an unknown. It's similar to our gas laws where we look and we write down our givens, we look at the question, we isolate the thing we're looking for, and we move on. So according to this little simulation section, what are we solving for? So it's there in bold. Look in bold.
Specific heat.
Of the metal. I'm going to do metal X on the simulation. So if you're on the simulation, you can pull up the little calorimeter that's there. We're going to solve for the specific heat of metal X. We're going to solve for C is what that is. So I'm going to use my whiteboard to do a part of this so you can see everything. Okie dokie. And here we go. So I think this is the generic setup. Yes, okay. So what you'll notice, it gives you, I think metal X needs to be highlighted. So you can do this with me as we go. So there's metal X. Kendall, what's metal X is mass? What's it say on the problem? You might need to pull up yourself. It's probably too hard to see that. Maybe Ethan can help me. He's in the front.
I got 20 grams.
Me too, right? So that's kind of the default right here. Do you see that right there? Everybody? Okay? So you're seeing the 20 grams. So write on your paper, and this is, I'm doing a part of the simulation for you. So work with me, okay? If you're not writing, you're not doing it right. You have to pick a pen, use your hand, fine motor control. Okay. Alright, so mass is 20 grams of the metal. I'm defining everything about the metal first. Austin, what's the initial temperature of the metal? 20 degrees Celsius. So put Ti, or T, temperature initial, is 20 degrees Celsius. And I don't have final yet, so I haven't even allowed this whole experiment to occur. Chris, what's the water's mass? Can you see it online? No? Okay. 30 grams, okay? What's the temperature, actually, I can't do it like that. Let me change one. I gotta change a variable, because do you notice their temperatures, initials are the same? Is it gonna change temperature? No, it's already at thermal equilibrium, so I'm not gonna have a process here. I'm gonna change the metal's temperature to 172. So change your temperature to 172 for your temperature initial. Okay, Carrie, what's my temperature initial for my water?
Your temperature initial is 20 degrees Celsius.
Perfect. Okay, sorry. It's a cat. Never mind. All right, so what? Oh, we didn't write this down on the simulator information. Do you see what it says about water here?
Heat capacity for water is 4.18.
Yeah, and I'm gonna go one word further. The specific heat capacity, that's what C stands for. Specific heat capacity is 4.18 joules per gram degree C. That's for who? Water. So C is 4.18 joules per gram degree C. That kind of looks like one of those weird units, like what? With the whole stacked units.
Oh, molarity.
0.0821. 0.021. That's kind of like the R constant, because it's got those funky units where there's a numerator and denominator. Kind of same story. Yeah, 4.18 joules per gram degree C. Okay, so now we're going to let this baby run. We're going to hit, now that I've got all my variables decided upon, hit start. And so you basically put this little chunk of metal in, and it starts you off at an originally 20 degrees Celsius of the water. And then what's happening? What's rising? Of the water, okay? And what's happening to the metal's temperature? It's dropping because heat is being taken away from it. It's being transferred. So a lot of common sense here, right? As the metal gives away energy, the water is gaining it. Where does it stop? What temperature? No, you see right there, it's kind of wavering, but 31.4. 31.23. Oh gosh, it's changing. I just have to take a temperature final. Okay, so 31.43 it is. Okay, so that's the metal and the water's final 31.43. Why is that both of their final temperatures? Thermal equilibrium. They stop at the same temperature because if they didn't stop at the same temperature, they would keep changing heat, and they're done. They are done. All right, are we done with the simulation part for now? No. We're done with this part for now. We gotta finish the calculation. Okie dokie. So now we already decided that we could set MCAT equal to MCAT, right? Because the Q, the heat loss, is the Q gained or the heat gain. So because we agreed on that, I'm assuming you are hunky-dory and you're good. Who in this case is losing energy, the metal or the water? The metal. So label, I'm just going to put negative MCAT and put a little M on the outside to call that the metal, so identify that. And who's gaining energy in the case of water? So put a parentheses around your MCAT over here, and let's just call that H2O to identify we're talking about water. Now, which of these lovely 6 variables are we solving for? So what do we not have?
Specific heat of metal.
Gases. The what?
Specific heat of metal.
Right, we don't have C for the metal. We don't have the specific heat capacity for the metal. So over here, MCAT equals MCAT, I'm looking for the metal's specific heat capacity right there. That's what I'm looking for. How do I get that by itself? Divide by what? Not just the m, but the negative as well, because right, we don't want the negative over there either. So I'm going to divide by what? Negative m delta t, or negative mass, and that's of the metal. I'm going to put a little m out there, bless you. And if I divide it on this side, I have to also divide on this side. Same story, divided by negative m delta t over here, and that's from our metal. So have I successfully isolated C? If I cancel out what I can, right? I can cancel out the negative, I can cancel out this mass, I can cancel out this delta T. You see C now is isolated? See, Kendall said yeah, anybody else? Okay, so C of the metal is equal to all this. But look how nicely labeled it is. All that junk on the top is for water. Where's that in the chart over there, left or right? Right, okay. All this right here is for metal. Where's that in my chart? Left. So keeping your data really organized is so helpful, and then it's not just a piece of cake after this. I just gotta plug in numbers. So here we go. We're gonna take what's the M over there referring to?
Water.
Mass of water. What's the mass of water? 30.0 grams. Okay. And then what's my C of water? Degree C, right? What do you notice we did not do with temperature here? Oh, hold up, I'm not there yet. I did not go to Kelvin. So here's where you have to break your mind, okay? Sorry. Gases relate to the kinetic molecular theory, and that has a little detail in it that says gases, speeds, and temperature must be related to Kelvin. Now, we're not dealing with just gases, we're dealing with all kinds of things here. So we are allowed to use Celsius when we're doing thermochemistry, but we have to use Kelvin when we're doing gases. Okay, so it's how the theories roll. So if I ever give you anything with delta or with a temperature, do think, am I using gases? No, I'm good, I can use Celsius. Yes.
Also, the difference would be the same.
It does, yeah, it really doesn't matter. It's just many times you'll see this constant with a delta degree C in it versus a Kelvin. You'll see it both ways, but I try to keep that division in your mind so you're not wasting your time converting Kelvin and Celsius, or with thermochemistry. Okay, so let's get this one as well. So we got mass, we got C. How do I get delta T? What did it say you had to do? Say again? Final minus initial. So for the water, I have to do final minus initial. Final is 20. I'm sorry. Final is 31.43 minus initial, which is 20. So what's the difference? 11.43. So it went up by 11.43 degrees Celsius. Okay, let's go ahead and calculate that before I put the numerator, this denominator down. Can you guys calculate that? Yes. Go for it, Carrie.
I'm gonna work it out here, but 14,
What?
That's what I got.
Okay, so here's the number. Chris, you with me? Jonathan? Chris, you guys with me? Okay. So Chris, maybe from there you can tell me this. Can you tell me what units cancel in the numerator so far? The grams here and here, and the Celsius here and here. Top and bottom. So what's this unit, Joe? Joules. J for joules, right? Okay. So we have the numerator calculated already. Now let's plug in this data for the denominator, and that's all regarding metal. Jess, what's the metal's mass? 20.0 grams. And oh, I forgot the negative. You see this negative right here? Don't forget to carry it down here with you. I do that constantly. How do I find delta T one more time? Final minus initial. What's my final over here? 31.4 minus initial, which was
Negative 172.
that says 17.
172.
Sorry, 172.0. So we're doing a small number minus a big number, so that's going to give us a negative number, and it should be because it dropped in temperature. It should be negative. What's that? What is that value, by the way?
Negative
140.57. Is that what you said?
Yeah.
Okay. We are done, basically. Almost. Kind of. Okay, so we're going to take our numerator value divided by our denominator value. What's 20 times that? Come on, don't mess with me. 2,811.4. And what units are here? And Celsius, right? Nothing canceled? You see? Okay, so that's grams and degrees Celsius. So when I take this divided by this, I'm going to still end up with joules over grams degrees Celsius. So take that, divide by that, what'd you get? Okay, 0.5098 joules per gram degree Celsius. That's the answer. That's C.
No, that's all we do?
Yeah. I mean, it took a little bit. This is actually, I'm gonna be honest, this is probably one of the hardest parts of thermochemistry because it has 6 variables to kind of make sure you keep track of. I wanted to show you this first because you kind of already know a lot, like, hey, heat's transferred, and one loses and one gains. And so that idea is not new to you. It's just now we're doing the math with it, and that's where we get information. Give me 1 second. So, before I lose your attention, that was the specific heat capacity of metal C. So on this, that I already did metal C. So use a simulator, calculate the specific heat of metal Y. What would differ here if you set up the same parameters? You set up the same masses, you set the same initial temperatures of 20 and then 172. What would be the only thing that would differ?
Final temperature.
Probably the final temperature, which would mean what would differ here?
The bottom grams degrees.
No, what data point, if temperature final changes, then what, the change in temperature, delta T would change. So this value, which is the delta T, and this value, which is the delta T, those were the only 2 numbers that differ. So do try to construct it very similarly, that way you get that practice in, okay? All right, I have one more thing for you. So I need to make some adjustments to deadlines because we have a lab on Tuesday, and we're burning food. And so you say dang it?
Yeah, food's delicious.
Oh, thank you. I thought you said dang it. Those are 2 different things. Give me 1 second. Hold on. I'm getting a lot of commentary, but give me 2 minutes right now to tell you what we're going to do burning food for. So you know in your body, you put food in your body for fuel to burn through aerobic respiration. So I need to know what food you put in your body for 4 days. Okay, Friday, today, Saturday, Sunday, Monday. Okay, and that's an easy grade. Actually, you're just documenting what you're eating, and then let me tell you why you're doing this. I really don't want to have to hold you after class, guys, on a Friday, so work with me, okay? So I have this link already under homework for Friday, and it does start today because I want to make sure you have everything done by Tuesday when we start the lab. But it requires you to either download the app, which is the MyFitness app, or there's a lot of apps that you can track nutrition or track what you eat and fitness on there. There's one called Lose It. You might have to delete something off your phone to get the app, or you can go on myfitnesspal.com and you can do it all online. But basically for 4 days, you'll be tracking what you eat. And as you track what you eat, there's a couple of interesting things on MyFitnessPal. It actually makes you set up an account with your level of activity. It's like, oh, Jonathan, you should have 2,500 calories a day. And you're like, okay, that's what my goals are. And it has different, based on your sedentary lifestyle or active lifestyle, it'll give you that information. So you can kind of see there's some little basics here. If you don't put down everything, I get it. I just needed to know this information right here. Then you already are on your A game. I want it to be Monday, Tuesday, Wednesday, Friday, Saturday, Sunday. Don't ask me more questions for a second. Let me finish this. So for grading purposes, creating the account is 10 points. That's easy. And it doesn't have to be MyFitnessPal. It can be another one. Just make sure you document it. The complete records of what you intake. That's the other part of the half that grade. And then the reflective component, which is there's 5 questions at the bottom of this. Just make sure you reflect on what you ate and what they kind of suggested. So based on caloric intakes, we are talking about calories, so we're talking about calories in terms of energy, which is what we'll be burning food for to determine if the calories they say are actually what's in there. So kind of just some personal information, personal reflections. The very last question is where you get your most money. Write a healthy paragraph on how this assignment relates to chemistry, Don't be shy, really dig into it. 6 separate accounts of explanations will give you your full 30 points. So most of it is, I can track it on my phone, that's easy, and then a 30-point reflection.
Where is all that?
Under this is under homework for Friday. Okay. So this is under homework for Friday. So what is it going to be due on Monday? I'll tell you, unless you want me to keep the due dates the way they are.
No.
Okay, so hush. Okay. So in terms of what I need from you, Monday will be the 4th day of this, and I'll get it from you on Tuesday. So Friday, Saturday, Sunday, Monday, and then because I won't be taking up on Monday, I'll be taking up on Tuesday. But the web quest itself needs to be done on Monday. Okay, that's going to give us a chance to actually do some of the calculations together in class, so you don't have to do them at home. CK12 stuff, if you get a chance to knock out some of that, I get it. If you don't, I can give you more time in class. However, do make sure you're addressing those small things you can, like sitting in front of the TV, doing nothing, click, 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 try out a couple of those. So if I don't have that, I'm not going to change the deadline on CK12 itself because I'll have to go through and change it for everybody, but I'm going to see how far we get, okay? So put that on the back burner, put the web quest on the front burner. Any questions right now? Yes, sir. Why? I mean, you can, what's going to happen naturally is that you naturally will as soon as you start tracking it. Because once you start going, oh man, that thing had 12,000 calories in it, maybe I shouldn't eat that. So it's naturally going to probably cause you to reflect. So like, something might, like from the standpoint of, oh, I ate ice cream. Like, oh, and then like,
Whatever you do, no one.
yeah,
No one order whatever big smoke order or brand that's going to take great. If you order like what 6 things? Like in theory, it was like like there was a theory about what you got.
I was wondering zombies the whole time. Come here.
A website, the guy actually found out what he ate.
I was doing that. He ordered it all. I was there too.
And he
I know.